What's that? Is this darker than usual, or it's only me? It's dark. I'm not sure. Can you read this up there? Yeah, it is dark. I have no idea what. Any ideas? It looks good on this screen. Well, I'm going to continue this way. Hopefully, it will become brighter. No idea what to do. So let me know if you stop seeing something. So, okay. So just hopefully you all had a very good break, and you're ready for the rest of the short rest of the semester. So I'm sure you all remember that next week we have the final in class. In principle, we cover everything from the beginning of the semester, as I said, with a focus on what we've done since the exam. On Thursday, I'm going to review what we're going to cover. The current plan is actually to solve a couple of problems and use this as a way to review some of the topics. If you have specific requests, please send me email as early as possible. Homework 7, due also on Thursday. This time we only give you 24 hours of additional time, if you still have additional time, because we want to give the solutions by the end of Friday. So you have time to look at it before, with enough time before the exam. Final projects, also notice that it's going to be by email to me. And please cut and paste this string. Don't type it, because whenever you type it, about a third of you type something else, which my rules don't catch. So, okay. And one other thing, my office hours today won't be the usual time. It's going to be later in the late afternoon, starting at 5:15. Questions? Okay, so I want to spend this basically almost last lecture on another topic. And I'm going to start by asking you how many. question means that you choose a number that makes sense given this question and the slide. I hope you can see it. And then say this number out loud. That's the protocol. 100, okay. That's a good number. Another number. 3. Another number. Who votes for 100? 1 vote over there. Who votes for 3? There's more votes for 3, so 3 is the winner. So that's, I would also probably choose 3, although 100 or 150 or however many points here is also a legitimate answer. And this is the problem of clustering, which is a very ill-defined problem in many respects. Nevertheless, when you see it, you know it. So 3 makes sense here for some reason, maybe for this reason. But really the goal is to figure out how to organize the data or into some sensible groups. So it's really, I mean, we categorize it as an unsupervised learning. Really, it's not a learning problem. It's more an optimization problem. And the question is, what do we want to optimize? We're really after some good way to organize or split the data into natural categories. And the study of clustering is a study of algorithms and other representations that are related that will allow us to do it. So I'm not going to have time to cover everything that people have done and will do in clustering, but I want to highlight a few important ideas in clustering, a few algorithms, and just so that you'll be able to think about it, because it is a very, very useful set of techniques. So if you think about it, I mean, a lot of you have thought about clusterings, but recently people often don't think about clustering this way as points in space, but they rather think about it as a collection of words that they want to cluster or collection of documents that they want to cluster. And they don't necessarily think about it as, well, really what I have is points in some space, and there's some natural distance between the points, and maybe it looks like this, actually. But regardless of how you want to think about it or what's your motivation, this is how it looks. I mean, you're going to embed it in some space, and you're going to play, or your algorithm is going to play with distances or similarities between these points. And you want to be able to think about how to aggregate these points in a way that the distance of points within a cluster is small, and the distance between points across clusters is large. And if there are some structural issues that have to do with the clusters like there are here, you want to be able to write an algorithm that captures this somehow. So the issues are there irrespective of how you think about it. As I said, people say that you recognize a cluster when you see it, but it's not so easy to come up with good criteria or kind of hard rules of this is the way cluster should look. And as a function of this, algorithms vary, and it's not easy even to evaluate sometimes. And one reason could be that given a set of points, you can cluster them different ways with different purposes in mind. If you think about it with this in mind, you can think about shape, size, density, a few other things. Okay, so here is another set of examples. And again, I could have asked you how many, and the same kind of problem arises here. I mean, you can think about multiple ways, and each algorithm that you'll come up with will succeed on some of these and fail on some, and definitely fail on others. So these are all difficult examples for all existing algorithms. And again, always think about the fact that even if you have other creatures that you want to cluster, at the end it's going to boil down to this, where when I put points on the board today, what I mean is that the Euclidean distance represented in this two-dimensional space is the distance, right? So if you think about this and try to dream up an algorithm that actually clusters it, probably you want to do it each line separately, especially if I tell you two. It's not so easy to come up with this because it's not only density, it's not only distances, it's some global idea that has to do with global properties of the set of points. Okay, so why is clustering so hard? It's because it's not so easy to come up with the optimization rules that you want to follow here. So given a set of points and a pairwise distance, our goal is going to be to devise an algorithm, or eventual goal is going to be to devise an algorithm that splits the data so that it optimizes some natural conditions. And the question is, what will these natural conditions be? And here are some suggestions for natural conditions. So let's just go over these conditions. So the first one here says scale invariance. For every distance function d, for any positive alpha, I want that the function relative to d is the same as the one if I scale it by constant. Makes sense, right? So if you have a good clustering function and I scale the distances by 2, should be the same clustering. Hopefully everyone agrees with that. The second one is richness. And richness says that I'm going to assume that the range of f is equal to the set of all partitions of S. So I can, depending on the function that you give me, I should be able to partition the set of points in any way I want. So I'm just saying this a little bit more explicitly. Suppose we are given the names of the points, indices of the points, but not the distances between them. Richness requires that for any desired partition, there exists a distance function that gives this partition, which also is a natural condition that you won't have. 3, written in a complex way, but actually is a simple condition, is consistency. Assume that d and d prime are two distance functions. And let's assume that gamma here is the partition that I get using the distance metric d. And let's assume that the other distance function, d prime, is a gamma transformation of d. What I mean by gamma transformation is that if the clustering gamma arises from d, and I generate d prime in the following way, reducing distances within clusters and increasing distances across clusters. That's what I mean by gamma transformation, a transformation that respects my partition. Again, I'm taking the resulting partition and I'm shrinking distances within clusters and I'm increasing distances across clusters. So then, by consistency, I mean I want that this d prime gives me the same clustering. Again, I think something that makes a lot of sense. So these are 3 natural conditions. And you may want to say, okay, so at the beginning you said you don't know how to impose natural conditions on your optimization function. Here are natural conditions. Now we know what we want to optimize. The problem is that actually you cannot. There is no clustering function that maps a set of points into a partition that satisfies all 3. Which is interesting. Now, of course, you can now think about, okay, which one are you willing to give up? And people have asked this question, and I'm not going to address it today. This is just to give you an idea or an intuition that clustering really is, in many respects, ill-defined. And you have to think a little bit about it. So what do we do? Basically, what we do is we develop various heuristics that make sense, do not satisfy all 3 conditions, but as I said, make sense. Sometimes clustering is done under some generative model assumptions, so we assume something about how the data is being generated, and this helps us to to develop a clustering algorithm, and I'm going to give at least 2 examples for that today. In fact, one we've already seen. So, so the rest of what I'm going to do today, now that you're convinced that it's somewhat ill-defined, is to give you some recipes and some of the key ideas and difficulties that they bring up. Now, of course, a key component when we do this is we have some measurement space. We put the points in some space. I don't want to call it a metric space because it's typically not going to be a metric space. And the question that we're going to ask when we do this is, what are reasonable distance or similarity measures? I'm going to use this interchangeably. The only issue for you to care about is that I want to minimize distances within clusters, and I want to maximize similarity within clusters. So what are the important dimensions of the data? Sometimes you don't care about all the dimensions of the data. And I'm going to talk about clustering methods and with connecting it to something that we've already done in this class, which is just learning, in the context of learning distance metrics. And in fact, I'm not going to get to talking about dimensionality reduction, but I think what I'm going to say about clustering will occupy today. So, okay, so just to remind you, I mean, we're given a set of data points. Each data point is assumed to be a d-dimensional vector. I'm going to write it this way. I'm not going to make, in principle, any statistical assumption of the data on the number of clusters or anything. So essentially, when we study clustering, you can think about me giving you this matrix of data points, and in this cell is the distance metric between these. Now, there's a lot of things one can say about distance metrics, and I'm not going to say most of them. I'm just going to highlight a couple of points. I'm assuming that you all are familiar with various distance metrics. The first thing I want to say is that for the purpose of clustering, typically the distances we are working with are not going to be metrics. Typically, they will not satisfy the triangle inequalities. Often, they will not be symmetric. But we're still going to call them distances. So again, there are a lot of distances that you're familiar with, you know, Euclidean distance, and I'm writing here, you know, Euclidean distance or L2, Manhattan distance or L1, infinity distance or L infinity, and a few others depending on the domain. And I actually want to highlight just one, in this context, one interesting property. So these metrics are different. But, you know, we know that they are ordered some way, right? So we know that L infinity is always smaller than the Euclidean distance, smaller than L1. The interesting thing about distances, and sometimes something that you want to think about, and this is property 1 that I want to highlight, is that they do not preserve order. So, for example, it could be that in one distance metric, C and D are closer than A and B, and in another, C and D are farther than A and B. So maybe you don't care about it because you only have one distance metric and you know that this is the right one for your domain. But as I'll show a little bit later, it's often important because there is a strong coupling of algorithms and distance metrics. It's not the case that algorithms that you use are independent of the distance metrics you use. And therefore, it's important to know some of these weird things that could happen when you change metrics. So this is one. So as we'll see, clustering can be sensitive to the similarity, and you want to, sometimes you want your distance metric to satisfy some other properties. For example, in some contexts, you want it to be invariant to some of the transformations that are natural in the problem. Sometimes you want to be able to blow up points, and you don't want the distance metric to be sensitive to this. Sometimes you want to translate points, and you don't want to be sensitive to this, and so on. And several of the metrics, again, I'm not going to go into the details here because I want to get to more interesting things, can be designed to be, for example, shift and scale invariant, rotation invariance, whatever you care about. So let's skip this. Okay. When we talk about distances, eventually we're going to use the distances in order to group points into clusters or group, and therefore we'll have to define also distances between groups of points. Here is a natural way of doing it. So let's assume that you do have a distance metric between 2 points, x and y. You can use it in a natural way to define a distance metric between a point x and a set A. I'm just averaging here over all the distances between x and points in A. And I can also define a distance between two sets of points. And I'm doing the same thing. I'm taking all the distances between points in A and in B and average. It's not the only way to do it, and I'm going to actually suggest that there are other ways of doing it, but we always want to be able to do it because as part of a clustering algorithm, we should be able to measure distances between sets. Okay, so now that we have this, I can develop an algorithm, and I'm going to give you the simplest clustering algorithm possible. You know, probably if you had to think about a clustering algorithm in 5 minutes, this will be the algorithm that you'll come up with. And in fact, it's quite effective, even though you'll see immediately that there are some downsides. So here is, but it will give us kind of an idea of what happens in clustering. So here is the algorithm. Input, I'm going to be given a set of endpoints. I'm going to be given a function, a distance function, and I have some threshold, fixed threshold, t. Ci is the Ci's are going to be the clusters, and for every cluster, I'm going to have a representative of the cluster that I'm going to call Zi. So I indexes into the data points and j into the clusters. Here's an algorithm, right? So really the question is, here's a point, where should I place it? And I'm going to start by initializing centers for the first cluster. It's going to be my first point. K, number of clusters, is going to be 1. And sequentially, what I'm going to do is I'm going to compute dij, which is the distance between the ith point and the jth center, representative of the jth cluster. And then I'm going to call di the minimum over all j's of dij, right? And I have a set of indices, which are the selected points. Di is the selected j's over dij. So essentially, what I'm doing here is for each point I, I'm finding the cluster. Now, I have two options. Either I place the point into its cluster, if it's close enough to the center of the cluster, or, and which I measure using this t, or otherwise, I'm starting a new cluster. So I'm increasing k. I'm choosing this first point that I decided it does not belong to any of the existing clusters into another cluster. So it's going to be the zk plus 1, the center of the k plus 1 cluster, and that's it. So I have an algorithm, very simple. Essentially, it says start with a cluster, check all the points, decide which cluster is the best cluster for them, look at the distances that arise, or the minimal distance. If you're happy with it, place it there. Otherwise, this point is going to start a new cluster. Very simple algorithm. What is the key problem with this algorithm? One problem with this algorithm. Yeah? How do you know the threshold is a problem? One more problem. The order is a problem, right? So really this is sensitive to how I start, right? So it really depends on how I order the points, and you want to get rid of this. But still, it's a clustering algorithm, and it gives you some ideas of what happens. So notice that it's also a very, very local algorithm. At no point I really look at everything. I do it very locally. So really what we want is we want to be able to think about some global metrics, which I'm calling here association and dissociations. Given a collection, I I want to be able to think about a measure of similarity within a group of points and a measure of similarity between different groups. And what I want is that when I define a group, the global association of points within this group is small, or high similarity or small distance, and across points, the distances are large or the similarity is small, right? So I want to define these metrics, these measures, in such a way that the within similarity can be maximized and the between similarity can be minimized. Everyone agrees that these are the desired goal, the desiderata for clustering. Now, it's going to, as you will see, it's actually not easy. Just like the slide that I started with, even these very natural conditions are not always easy to accomplish. In fact, we're going to get to it only at the end. Most clustering algorithms cannot achieve both of these together. And again, you can think about this here, and it's not completely clear that this by itself, even though it sounds nice before I show this, it sounds as nice after I show it, because these do not capture structure, for example. Okay, but it still gives us an idea of what we want, and I'm going to follow this with some definition that will allow us to measure the quality of our clustering. And in the next clustering algorithm, we're going to use this. So this is how I'm going to define it now. I'm going to define two definitions that are called scatter measures. One of them is a within cluster measure. So really, you can think about it as the average distance to a representative. So remember that these were my representatives. So I'm going over all xi within my cluster, within the jth cluster, and I'm looking at the distance from xi in the cluster to its representative, and I average over the size of the cluster. So this is a within cluster measure, right? And if d is a distance, I want this to be small. And I can also think about some global clustering metric, where here what I'm looking at is I'm looking at the distance between each point, all the points, m points, xi and zj. I'm going to find the minimum one, which means I'm looking at, for xi, which cluster is the closest, or which center is the closest, right? Minimum over j. And I'm averaging this over all the points. So for each point, I'm finding the closest center, and I average over the point. So this is some kind of metric that gives me a global view of how scattered this cluster, this specific partition is. Now, let's assume that for each xi, I've chosen the closest representative. Under these conditions, dj really measures the scatter of the j's cluster. It's just a within cluster metric, and I want to minimize it. And d here measures the quality of the clustering. Yeah. In principle, yes.
So how is that telling us the distance between?
Well, but when I do this, I still don't know that I've achieved this. So you have a bunch of representatives, and you have a bunch of points, and the question is, what's the right way to place the points into the clusters? So what this does, it measures how successful I am. If you placed all the xi's to the closest zj, you could say this is probably a good clustering. If you haven't done that, probably not a good clustering. And that's why D, you can think about it as measuring the quality of the clustering that you've done, the quality of the partition. So for optimal clustering, as you said, yes, xi is going to be in the rth cluster if zr is the minimum over all clusters of the distance between xi and zj. This is basically what you said. And that means that I've done a good job. And under these conditions, you can do a little bit of algebra and say, okay, so what is D? We define D to be this way, right? So I'm taking all the points, 1 to m. For each one, I'm finding its zj. And I'm averaging. Now, because I've clustered well, that means that I can replace the sum of m here with just multiply this both sides. So you'll get size of Cj times dj, and you again have the sum over all points separately for each one of the clusters. So they are going to be equal under this condition. And I can just rewrite it this way. So basically, it tells me that for optimal clustering, this is the right thing to do. And it also gives me an idea, what do I want to minimize? So if you have a clustering algorithm, whatever clustering algorithm you have, you can use this as some kind of a stopping criteria. It tells you, well, now you're doing pretty well because you've minimized this quality of clustering metric. And we can use it in various clustering algorithms, and I'm going to show it now. And in fact, it's being used in the context of, for example, k-means. Yeah.
So can we go back to 2 slides?
2 slides.
We said that one can minimize the within.
Yeah. This one?
Yeah, here it says that within similarity.
Okay, so as I said, I'm using interchangeably similarity and distance.
But the within similarity, should it be minimized or maximized?
Similarity should be maximized. The distance should be minimized. So I'm going to keep you on your toes. So I'm going to use both similarity and distance. Okay, so here's an algorithm. And the reason I introduced this D before is because I'm going to use it now as my stopping criteria. I have a quality, I have a way to measure quality. Question? Let's ask the question again after this algorithm. So this algorithm is going to do this. So here is another clustering algorithm, significant improvement over the simple-minded one that I presented before. I'm going to initialize centers randomly. So now the input, okay, I have to say this. I have a set of points. I have a distance function. In addition, I also have k. Someone told me, I want you to cluster this into k clusters. Oh, this sheds some more light on this also. Interesting. Some new features here. Okay. Okay, so I know that I'm expected to have k centers, so I'm initializing k centers randomly. Then I'm clustering with respect to these centers using nearest neighbor, just like before. So I'm placing xi into cj if j is the argmin of the distance between xi and zj. So essentially, take xi, check the distance to all the centers, choose the minimal one, place it there. Now, to your question, I'm updating the centers. How do I update the centers? Now I have all the points, x1 up to xm, split into clusters. In each cluster separately, I'm choosing a new center. I'm choosing the zj that minimizes the metric that I suggested before. Remember, dj was this metric, which is the average distance to the representatives. So I'm choosing a new representative that minimizes this. So I'm going to go over all options for ZJ from within my cluster, and I'm going to choose the one that minimizes this. Up. Choose ZJ to minimize DI. Is that clear? This is essentially a search procedure over my cluster, over each cluster separately. Now that I have this, I can compute the D again. Right? Again, let's recall. When I compute the D, which is a global clustering metric, I already know for each cluster what is the representative. And I'm basically looking at each point, and I'm asking what's its distance to each one of the centers, and I'm averaging over the points. So I chose new centers in 3, and I'm computing the quality of the current clustering. I'm going to call this the quality of round R. My stopping criteria is whether I'm improved. So dr minus 1 minus dr divided by dr minus 1 is less than some threshold. Okay? If not, I'm going to continue. Otherwise, I stop. So this is an algorithm that should be familiar to you. At least a version of it should be familiar to you. Notice, what am I doing? I have some guess of the centers. Using this guess, I'm splitting the data. Once I split the data, I choose new centers, and I keep on going, which is the EM algorithm that we talked about a couple of weeks ago, only that it's a hard EM algorithm, unlike the one that I described before, which was a soft EM. But in the soft EM, we did not assign each point xi to a cluster Cj, but rather we had a probability distribution P of Cj given xi, which says, well, 0.3 of xi is in this center, 0.2 of it is in this center, 0.1 of it is in this center, and so on. Here, I'm just choosing a center based on this argument. That's the difference. In EM, once we did this, we again estimated the new centers. Right? This was our E step. So because it's really an EM algorithm, we know that it's going to converge in the following sense. It's not going to converge necessarily to a global optimum, but we know that every round, the scatter mean is going to go down. So this D metric that I suggested before, which was, again, what I estimated here, the clustering, the total scatter of this is going to go down. Maybe it's going to go down a little bit every time, so I want to stop it at some point because it's not productive anymore, but it is going to go down. What we don't know, of course, is how many rounds are needed. Again, it's an EM algorithm. So that's one. Now, one question that you can ask, or another question you can ask about this algorithm, notice that the way I described the algorithm, the center was an element in the set. Right? I started by choosing random representatives. And every time after I split the data into clusters, I went to each cluster and chose a new representative. Right? I chose a new representative by minimizing this DI. You don't have to do it necessarily. Again, it depends on your application and your domain. In some cases, for example, if you're using Euclidean distance, rather than doing this optimization problem, trying each one of the elements and deciding whether it's a good representative or not, you can just compute the average of the data points in the cluster. This average is not necessarily one of the data points, but still, it's a good representative because it's a centroid of this cluster. And this is also computationally much, much easier. Again, if you go back to the k-means algorithm that we presented as an EM, that's what we did. And we showed that this was the right thing to do because averaging under the Euclidean distance is the most likely estimate of the center. Okay. Final question here is, what is k? Same question that we had when we did k-means as an EM algorithm. We assume that k is given to us, and you can get around it in many ways. You can get around it using search. You can get around it by assuming another probabilistic model on top of this. There are algorithms like isodata that kind of is k-means plus plus with a lot of other provisions for things, including adapting k. But this is really the most fundamental and still probably in most cases the best algorithm you want to use. Okay, so as I said, it's a good algorithm. Under some assumptions, it's the best thing you can do. If the assumptions are, for example, a mixture of normal distributions with Euclidean metric, this is the right thing to use. Under many other assumptions, it's also the right thing to do because it has this appealing property that it's related to some generative model over the data. Okay. Key limitations, of course, is that are structure limitations. So often, if you have different structures, internal structure of clusters, this algorithm is not going to exploit it well. And these are just some examples that a standard k-means with Euclidean distance, of course, is not going to capture. You won't be able to get this. So you need some more. So before I get to a few other algorithms, I want to make one other interesting comment. I'm not going to give all the technical details here. So there is something appealing, as we said when we talked about k-means, about the fact that there is a generative model that is assumed, and as a function of these generative models, we derive the algorithm. You can actually do this for many other algorithms, it turns out, not only for k-means. So I'm going to call this model-based methods, and I'm going to give just a flavor of what we do. And the flavor is a class of agglomerative clustering algorithms. Again, a very natural class of clustering algorithms that goes as follows. You start with some distance measure between points, and as a function of this distance measure, you define a distance measure between clusters, between groups. I already defined it before, and I said, we always need this. When you do clustering, you start with a distance between points, but you need eventually to devise a distance between a point and a group of points, a point and a set, and between two sets. You can do it multiple ways. Before, what I did is just averaged. But you can imagine many other ways of doing it. And I'll give a few examples in a second. But let's assume we already have it. So I have a distance measure between clusters. Once I do this, I have the following very simple algorithm. I'm going to initialize each point in a separate cluster. At each stage, I'm going to merge the two closest clusters according to this new distance measure. And that's it. Right? So I'm starting with each point in its own cluster. And every time, I'm choosing 2 points, 2 clusters, and I'm going to merge them. And I'm going to repeat it until I'm satisfied under some criteria of being satisfied. You could use the quality metric that we had before if you want. Okay? So it's a family of algorithms that is parameterized by how we define this D, capital D, as a function of lowercase d. And here are a few options. So I already gave you one, just average. Here's another one. It's called the single link clustering. And I'm defining distance between clusters C1 and C2 as the distance between the minimum over all distances in the clusters between pairs of points. Okay? So I'm going over C1 and I'm going over C2, and I'm looking at all pairs, and I'm finding the minimum, and that's the distance between the clusters. If you think about it, for these two kind of weird set of points, I'm going to get good clustering here. But of course, it's not the only way you can do it, right? You can also do it with the max. I'm going to define the distance between C1 and C2. Again, I'm going to look at all pairs of points and defining the distance between the cluster as the max. And there are a few others. I can do it as the mean. This is the one I introduced earlier. I'm looking again at all pairs, and I'm going to average them. I can define something more complicated here that has to do with something that is called these ward methods. If you think about this, this is kind of an L2 metric within each set, and I'm doing it on C1, I'm doing it on C2, and I'm doing it on the union, and I'm looking at the difference. The nice thing about these different metrics is that it turns out that you can come up with a generative model so that clustering, agglomerative clustering, this very simple algorithm, according to these capital Ds, really is, really corresponds to a generative model over the data. And the next few slides, which I'm not going to discuss, explain how to do this. So again, the real value of this, for example, for word, this is the simplest, the most natural, essentially some kind of a Gaussian density function generates the data, and ward is the right metric so that agglomerative clustering does the right thing. So again, there is something appealing about clustering this way. One, agglomerative clustering is a very simple natural algorithm. Two, what you're doing is meaningful if you believe that the data was generated this way. So again, I'm not going to give the details. If you want to follow it, it's here. But it's somewhat cool that very simple algorithm or very similar heuristics can be given this probabilistic interpretation. Okay. I said that I'm going to talk a little bit about distances, and before I move to talk about other distances, I want to highlight one important issue that you always want to think about when you do clustering, and that's the fact that there is a tight coupling between the algorithm that you run and the distance metric. Let's look at these examples. So if you look at these two sets of points on the left, set 1 and set 2, it's the same data set. In both cases, I want you to look at the Euclidean distance. So the F's here are the coordinates. Think about it as features. So I'm looking at L2, right, Euclidean distance. If I'm running this using the single link algorithm, which I defined before, agglomerative with single link, if you think about it, you'll get this clustering. Black points, white points. On the other hand, with the same Euclidean metric, if I'm going to run k-means, I'm going to get this clustering. So same metric, different algorithms, different results. Now let's look at this set and this set. Now I'm going to run the same algorithm. In both cases, I'm going to run k-means, but I'm going to change the metric. Here I'm going to run it with the Euclidean metric. Here I'm going to run it with L1, linear metric. I'm going to get different results. And of course, I set it up such that this is what's going to happen, but this is the truth, right? So it's always going to happen. So there is no universal distance metric nor a universal algorithm. There is dependence between the distance that you choose and the algorithm, and you have to be aware of it if you want to think about clustering. Okay, so that's kind of part one of what I wanted to talk about. And then next I'm going to move to talk a little bit about graph theoretic methods. So in many cases, you actually don't care about the coordinates of the points. So you don't want to think about them as, I'm putting it into this Euclidean space or any other metric space. All you care about, or all you are given sometimes, is just relative distances between points. I know that these 2 points are similar, these are not so similar, and so on. I don't really know the coordinates of the points. And in these kind of cases, it's a very natural way to think about it is to think about it as a graph. The data points that you have are nodes in the graph, and the edges are going to represent distances or similarities between the nodes in the graph. So you have some kind of a proximity metric between the points. So, and that's what you have to work with. So a natural algorithm in this case is going to be to partition the graph, to partition the set of nodes in the graph in such a way that, again, let's say you partition it into 2 groups, you want to be able to say something about distances within this set of nodes and distances across 2 sets of nodes. So is this modeling clear? I mean, what I did is I dropped the assumption that I embed everything in symmetric space, and all I have is a bunch of points and relative distances between them. Now, again, this gives rise to a very natural way of thinking about it. So, of course, the questions are, what are the criteria for good partition, and how can we compute it? And a very natural way is just to think about, let's decompose the graph somehow. And here is a very simple algorithm to decompose the graph, equivalent to the first algorithm we started with. I'm going to take all the points. I'm going to build a tree over the points. I'm going to construct specifically the maximum spanning tree. Notice that now I'm working with similarity, right? So similarity means that I want to keep those nodes that have high value between them because they are highly similar, okay? So it makes sense to build the maximum spanning tree. You already know how to build the maximum spanning tree. And once I have this, I want to be able to eliminate some light edges and decompose the tree. What does it mean, light edges? You can, again, come up with multiple ways of defining it. It could be based on a threshold. All the edges that are below something, it's not similar enough to me, so I'm going to split them into distinct clusters. Or I can do it something relative, right? Delete an edge if its weight is significantly lower than other edges, and you can come with probably other idea. But algorithmically, a very simple algorithm, right? So you start with a connected graph, and then you split it. And again, I'm not going to give details. You can do it in many ways, but the key thing is that these methods are local methods, just like the algorithms we started with when we embedded points to space. In some space, it's the same thing, right? You don't really look globally at all the sets of points, but rather you look at 2 points and decide, should they be in the same cluster or not? And what I want to be able to get to is I want to be able to get to some more global methods. So I'm going to skip these next few slides that actually suggest to do agglomerative clustering, the same kind of clustering we talked about 5 minutes ago, only that now it's in the context of a graph-based method. It's the same algorithm. No need to talk about it. And I want to move to global methods. And again, this is an example that indicates that we want to be able to do something global, something that looks at all the data points at the same time. And the question is how to do it. The basic question is still the same, how to partition the graph into a natural disjoint set. And this is another example that you want to have in mind. You want to somehow capture the fact that, these really are lines. And the scale shouldn't matter. So we want to try to define a global degree of similarity between parts of the graph. So one way to think about it is to think about some degree of similarity between parts. So if I have two parts, A and B, the cut of the graph is the sum of the weights that go between A and B. I'm looking at all pairs of points, U, V, U in A, V in B, and I'm summing the average. So this is a metric or a function that is somewhat global, right? It looks at all the points together, and it's easy to compute. And the question is this going to be a good metric for me to drive my clustering algorithm? So, and just as a sidebar, I mean, I'm going to talk only about binary clustering here. I'm going to split it to 2 points. And if you want to split it to more than 2 points, you're going to do this recursively. OK, so let's look at these data points. And the question is, I'm going to define the cut. What will I get from the cut? Anyone has an intuition? You know what you want here. What will the cut give you? It turns out that it's not going to give you what you want. This is really going to be the cut. And the reason is, and you know, this is going to be the second best. And the reason is that really the cut value increases with the number of edges that go across partition, and therefore it's going to prefer to cut away a small set, because then the number of edges going out of it are going to be small. So it's not really what we want, even though we have a global measure, doesn't do what we want. Really, what we want is this. Right? We want to distinguish between high-density set and low-density set. So the way to get around it is actually to normalize. Very simple idea. Computationally, it makes things a lot more complicated, because cut is easy, and normalized cut is going to be hard. But at the level of ideas, it seems like a good thing. So I'm going to define a normalizer. And my normalizer is going to be defined as a measure of association between a set A and the rest of the graph, all the nodes, V. And it's going to be just as defined before. I'm going to sum all the edges between nodes in A and other nodes. So this really gives me the total connection from the nodes in a set A and the rest of the graph. And this can be used as a normalizer. So now I'm going to define the normalized cut between A and B. And it's the cut between A and B averaged relative to A, plus the cut between A and B normalized relative to B. Okay? So that's the definition of a normalized cut. And really, it gives me the way to measure dissociation between clusters in the graph. Okay? Now, with this, I can, so I define a measure of dissociation, but I can also define an association within cluster in, again, very similar way. So I'm going to define the association between A and itself as before, basically the total weights edges within a cluster A. And I'm going to now define a normalized association between A and B as the association between A and A normalized relative to A, plus the association between within B normalized. Okay? So I define two normalized metrics. And really, if you think about it, this is something that you want to minimize between A and B, similarity between similarity or distance, again. And this is something that you want to maximize, right? This basically tells you something about how tightly the nodes are within A and within B, averaged over the graph. So we are playing exactly the same game as we've played before, in the sense that we still have these two metrics, or two measures, one within a cluster and one across clusters, and we want to minimize the distances within cluster, or maximize the similarity within clusters, and minimize the similarity within clusters. I said it wrong. Let's say it again. I want to minimize the similarity across clusters, and I want to maximize the similarity within clusters. So let's do a little bit of algebra. So I'm going to start with this normalized cut, which I want to minimize, and is defined this way. Right? So again, cut between A and B, average normalized relative to A, and the same cut normalized relative to B. I can always write this. I'm going to split this cut AB as the association between A and all of B minus the internal association of A. Notice that this is exactly the cut AB, right? Because this is sum of all distances between A and all nodes, subtracting all distances within A. So I'm getting just the cut. Keep the same normalizer, and I'm doing the same thing here. Now, this is 1. This is also 1. So what I get here is 2 minus the association, internal association of A normalized, minus internal association of B normalized, which is what I get here. And this is what I called the normalized association between A and B. So the nice thing is that if you look at it, what we got is these two measures. The normalized cut that I want to minimize is 2 minus the normalized association, which I want to maximize, which means I can do this together. So if I have a way to minimize this, at the same time I'm going to maximize this, which is really what I want to do. So this normalized cut algorithm actually gives me a solution to something that we highlighted at the beginning and said it's hard to do. In this context, we actually figured out a formulation that allows us to do what we want. Of course, there are some problems. So on one hand, as I said, it's doing what we want it to do simultaneously. On the other hand, unlike cut, it's hard to compute. Normalized cut is an NPR problem, and people can compute approximation of this using spectral method, essentially solving eigenvalue problems, which in theory are easy problems to solve. In practice also, not always easy if you have a lot of points. But that basically is the way to solve it. Now, in practice, so this is actually a very, very nice algorithm, if you think about it, because originally when we started about an hour ago, it wasn't clear whether we can actually optimize what we want to optimize. And this is, as far as I know, the first algorithm that actually allows us to do this in a principled way. Computationally, it's not so easy. In practice, it turns out that it's not always the best algorithm. In many, many applications, you don't need to bother with spectral methods, and you can run k-means or even simpler agglomerative clustering for the same results and more efficiently. But nevertheless, in some application, it found really good success. Specifically in vision, often, these are methods that people are using. Okay, to summarize, we talked about clustering. I really gave you kind of a crash course in hopefully a few ideas that come up when you look at clustering. One, the problem is ill-defined. Two, how you define the problem, what features, what distance metrics is really going to make a difference. We talked a little bit about the standard approaches. These are really two important algorithms, very useful to Today we talked a little bit about graph theoretic method, focusing on cut or normalized cut. And still, some of the key issues that come up are scalability. You know, inherently, clustering is a quadratic method. You have to compare a lot of points. If you have 1 million points or 10 million points, it's hard to do. You have to think about how to do it. And a lot of the research today actually, again, depending on the application, deals with scaling up clustering algorithms. Another issue is the distance metric. As I said, and when I gave this example, the issue of what is the metric and what's the correspondence between the metric and your learning algorithm and your clustering algorithm is very important, because these two are tightly coupled. So I'm going to end with kind of closing the loop and talking again about learning, because we haven't talked about learning today. There's really no universal distance metric, but once you've decided which is the clustering algorithm you want to use, perhaps you can learn a better metric to fit your clustering algorithm. And there's been a lot of work that tries to embed this kind of generic paradigm of clustering within a learning scenario. So this is the generic clustering, right? So we start with an unlabeled data set. Someone gives us a distance metric. Someone gives us a clustering algorithm. And together, these give us a partition of the data, right? That's clustering. Now, and you can think about, you know, a specific distance metric, a specific algorithm that will instantiate kind of this box here. So this is unsupervised, no learning. A lot of work has tried to actually think about how can we embed this box of traditional clustering within a learning scenario. And you can think about a lot of reasons why you want to do it beyond the example that I've given before. Here's another example. Here's a bunch of points. I can tell you, you know what, k is equal 4. You still don't know how to cluster it yourself, right? Because there, for example, there's the way to do it vertically and horizontally. These are two key options. Maybe there are other options. But if I give you a few hints in a form of supervision of some of the points, for example, this, now you know how to cluster it, right? So I colored some of the points, and now you know that probably what I mean is this. It's going to be the horizontal cluster. So you can see the power of this in determining what is the distance metric here, right? Because here, basically, you say, I don't care about horizontal differences or distances. I only care about vertical distances, right? That's basically what this hint that I gave you implies. So the question is how to do this. So I'm going to give just one idea, very simple idea, that takes this and essentially embeds it within a learning algorithm. So the key idea is that I'm thinking about these two as my partition function, right? It's something that takes data, does something, results in a partition. I want to be able to train it, which means I'm going to add some labeled data set, or label some of the data. I'm going to have a supervised learning. And this supervised learning is going to allow me to train this box. The key thing really is how do I know that I made progress? Exactly the same question that we always have in learning. So I have my supervised partition. This is the supervised collection of points. And I have my partition that my current clustering algorithm gives me, this H. And I want to be able to measure the distance between them, or the error of H relative to P, and minimize it. So find the distance metric that minimizes the distance between my partition, the one that my clustering algorithm gets, and the supervised data. Of course, you can define this in many, many ways, and I'm not going to dwell on it. Here are several ways in which you can define it. But basically, the idea is you have two clustering of the data, right? So two ways to split data into groups, and you can define distances between them. It's not easy. Depending on the application, you may want to change it. This is in some communities, some of the big problems. What's the right way to define these metrics? But you can define it. I'm giving here a few options. Let's assume that I have this. Now, the question now is how to learn. And the question of how to learn really has to do with one key question: how to parameterize the distance function. But you can think about this. This is actually what we've done throughout the semester, right? So you can think about your distance metric as just a linear function, right? So you have dimensions, you have features, and what you want to do is you learn the coefficients of these features. They define a distance, right? Going back to this example, I have two dimensions: vertical distance, horizontal distance, and the fact that I annotated, color the point this way, essentially tell me that I don't care about the horizontal distance at all. Put weight 0 on the horizontal distance. Put weight 1 on the vertical distance, right? So I learned a metric that was a linear metric. And this, in general, is a pretty good idea. You want to parameterize your distance metric somehow. So in this case, what I show here is, again, a linear function. This is some function, some feature function. And these are weights for the nth feature function. Square root, if you want. And essentially, the algorithm that you get, we know how to learn linear function. You can run a gradient descent-based algorithm over this linear function within this box here. Right? So essentially, you give supervision. You got a partition H. You compare, and you want to minimize the distance between your H and the labeled data P. So we're going back to the same learning algorithm that we've done in the rest of the semester, learning linear function. And this is actually quite commonly used today as a way to learn distance metric. Again, the key question, as I said, is just how to parameterize your metric, which hypothesis space to use for your metric. Once you do this, you use everything you've done earlier in the semester. Questions? Okay, so I gave you a little bit about clustering, just to kind of get your imagination on this going, because there isn't a lot of time to talk about, and close the loop, showing that really you can use learning, whatever learning you've done earlier, to do it. Next time, I'm going to summarize, and as I said, if you have specific topics that you want me to cover, specific questions, send me requests as soon as you can. Okay, see you Thursday then.